Look up tonight. Go outside, wait for your eyes to adjust, and look at the sky. What do you see? Darkness. Vast, endless darkness, punctuated by a handful of bright points. A few thousand stars, maybe, if you're lucky enough to be somewhere without light pollution. The Milky Way, perhaps, stretching like a faint river of light across the black. This seems obvious. This seems like nothing. Of course, the sky is dark at night. The sun went down. We take the darkness for granted. We swim in it like fish swim in water, so accustomed to its presence that we never stop to wonder at it. The darkness is just there, as natural as breathing, as unremarkable as the air. But what if I told you that the darkness shouldn't exist? What if I told you that according to the best physics and astronomy of the 19th century, the night sky should be blazing with light, not just bright, blindingly, overwhelmingly brilliant, as luminous as the surface of the sun itself, everywhere you look, all the time? What if the simple fact that you can stand outside at night and see darkness is actually one of the most profound pieces of evidence we have about the nature of reality? Here is a question that haunted some of the greatest minds in history for over 400 years. A question so simple it feels almost embarrassing to ask, yet so profound that answering it required us to completely rethink the nature of the universe itself. Why is space dark? Not why is it dark at night when the sun is down? Why is space itself, the void between the stars, dark at all? Think about it. There are approximately 200 sextillion stars in the observable universe. That's a 2 followed by 23 zeros. More stars than grains of sand on every beach on Earth. Many of those stars are far brighter than our sun. They've been burning for billions of years, flooding the cosmos with light. So why, when you look up, do you see mostly nothing? This isn't a trick question. This isn't a riddle with a clever twist. This is one of the most important questions ever asked in cosmology. And for centuries, nobody could answer it, because the obvious answers are all wrong. And the real answer tells us something extraordinary about the universe we live in. It tells us that the cosmos had a beginning. To understand why this question matters, we need to go back to a time when the universe looked very different, at least in human imagination. For most of Western history, educated people believed the cosmos was infinite and eternal. It had always existed. It would always exist. Stars filled an endless void in all directions, unchanging, forever. This wasn't just philosophy. This wasn't idle speculation or religious dogma. It was what the best science of the time suggested. Isaac Newton, perhaps the greatest physicist who ever lived, believed in an infinite, static universe. He had compelling mathematical reasons for this belief. In 1692, Newton wrote to the theologian Richard Bentley about a troubling problem in his theory of gravity. If the universe were finite, if it contained a limited amount of matter in a bounded region of space, then gravity would be a disaster. Every particle would be pulled toward every other particle. Over time, everything would collapse inward, drawn by mutual gravitational attraction into a single, catastrophic point. But if the universe stretched forever in all directions, with matter distributed infinitely throughout infinite space, the gravitational forces would balance. Each particle would feel pulls in all directions, and those pulls would cancel out to zero. The universe could remain stable, unchanging, eternal. This was an elegant solution to a serious problem, and it carried an implicit assumption that would go unquestioned for 2 centuries. The universe has always been here. It will always be here. There was no beginning. There will be no end. The universe, in Newton's view, was a vast, eternal stage. Stars were the permanent fixtures, burning with some mysterious source of energy that no one yet understood, unchanging across the ages. The cosmos simply was, timeless, infinite, static. This picture of the universe was deeply comforting to the scientific establishment. It was also, in some ways, deeply terrifying. An infinite universe with infinite stars meant that humanity was utterly insignificant, a speck of dust floating in an endless sea of fire. But at least it was stable. At least it was eternal. At least the rules didn't change. But there was a problem with this picture, a problem that, once you see it, you cannot unsee, a problem that would gnaw at astronomers for centuries, demanding an answer that the static, eternal universe simply could not provide. The German astronomer Johannes Kepler saw it first in 1610. He had been reading Galileo's reports of countless new stars visible through the recently invented telescope, and something bothered him. Galileo was excited by the discovery. Each new star was evidence of the vastness and richness of creation. But Kepler felt a growing unease. In a letter to Galileo, Kepler wrote something remarkable. "You do not hesitate to declare that there are visible over 10,000 stars. The more there are and the more crowded they are, the stronger becomes my argument against the infinity of the universe." This was a strange thing to say. Why would more stars argue against an infinite universe? Surely an infinite universe would contain infinite stars. But Kepler understood something that Galileo had missed. In an infinite universe filled with stars, every line of sight should eventually hit a star. Look in any direction, up, down, left, right, at any angle. And if you could see far enough, your vision would land on the surface of a star. The geometry was inescapable. If stars go on forever, then in every direction, eventually, there is a star. And if every direction ends at a star, then every point in the sky should be as bright as the surface of a star. The entire sky should be as bright as the surface of the sun. Not just bright, blazing, incandescent, unbearable. Kepler knew this wasn't just theoretical. He could calculate it. If the universe stretched away endlessly, with stars like the sun swarming everywhere, then the whole celestial vault would be as luminous as the disk of the sun. Day and night would be meaningless. The sky would burn with infinite fire. Imagine standing in a dense forest, not just any forest, one that stretches to infinity in all directions. The trees are planted densely, but they go on forever. Now look around. No matter where you look, your line of sight eventually hits a tree trunk. There are no gaps in your view of the forest because the trees never end. The forest fills your entire visual field. Now imagine those trees are stars, and they're not just blocking your view. They're glowing, every single one of them, blazing with nuclear fire, radiating light and heat across the cosmos. The night sky should be blinding. The daytime sky should be no different. The entire universe should be a furnace. Kepler used this observation as evidence that the universe must be finite, that beyond a certain distance, there was simply nothing, a dark wall at the edge of creation. This was theologically convenient for Kepler, who served as imperial mathematician to the Holy Roman Emperor. Just 10 years earlier, the philosopher Giordano Bruno had been burned at the stake for, among other heresies, advocating an infinite universe with infinite worlds. Kepler had reasons to support a bounded cosmos, but the argument itself was sound. The mathematics were correct, and the question would return to haunt cosmology for the next 200 years, demanding an answer that no one could provide. The problem got a formal name in 1823 when a German astronomer named Heinrich Wilhelm Olbers published a paper that laid out the paradox in detail. Olbers wasn't the first to discuss it. The English astronomer Edmund Halley, famous for the comet that bears his name, had written about it as early as 1720. The Swiss astronomer Jean-Philippe Loy de Chezeaux had done careful calculations in 1744, but Olbers's name stuck, and we now call it Olbers's paradox. In truth, the puzzle goes back even further. The English astronomer Thomas Digges, writing in 1576, was perhaps the first to realize that if stars extended infinitely, the sky should be filled with starlight. Digges was a revolutionary thinker. He was the first to publish an English translation of Copernicus's heliocentric model, and he went further than Copernicus by suggesting that the stars might extend outward to infinity rather than being fixed on a celestial sphere. But Digges didn't have the mathematical tools to fully analyze the problem. He simply assumed that distant stars were too faint to see and left it at that. The mathematics of the inverse square law, which would show this explanation to be insufficient, weren't yet widely understood. Olbers was an interesting figure. He wasn't a professional astronomer. He was a physician, treating patients in Bremen by day and scanning the heavens by night. He discovered several comets and 2 asteroids, Pallas and Vesta, and he spent years thinking about why the night sky was dark. The mathematics he developed are actually quite elegant, and they're worth understanding in detail because they show just how inescapable the paradox really is. Imagine dividing the universe into a series of thin spherical shells, like the layers of an onion, each shell 1 light-year thick, centered on Earth. This is a thought experiment, a way of organizing our thinking, but the math works for any thickness of shell. In the first shell, the region from 0 to 1 light-year away, there will be a certain number of stars. Let's call it N. These stars are close, so they appear bright. Each one contributes a certain amount of light to our sky. Now consider the second shell, from 1 to 2 light-years away. Because of the inverse square law of light propagation, each star in this shell appears dimmer than the stars in the first shell. If a star is twice as far away, it appears only 1/4 as bright. This is basic physics, well understood since Kepler's time. But here's the crucial part. The second shell has a larger volume than the first. In fact, because the surface area of a sphere grows with the square of the radius, the second shell contains approximately 4 times as many stars as the first shell, assuming stars are distributed roughly uniformly through space. 4 times the stars, each 1/4 as bright. The total light from the second shell equals the total light from the first. Think about that for a moment. The second shell contributes exactly the same amount of total light as the first shell. The increased number of stars exactly compensates for their decreased brightness. And this is true for every shell. The 10th shell has 100 times as many stars as the first, but each star is only 1/100th as bright. Same total light. The millionth shell has 1,000,000,000,000 times as many stars, each 1/1,000,000,000th as bright. Same total light. No matter how far out you go, 1,000,000 light years, 1,000,000,000, 1,000,000,000,000, each shell contributes the same total amount of light. add up an infinite number of shells, each contributing the same amount, and the result is infinite brightness. The mathematics are irrefutable. In an infinite, static universe filled with stars, the night sky should be infinitely bright. Now, in practice, it wouldn't actually be infinite. Stars are not points, they're spheres. Eventually, nearby stars would block the light from more distant ones, just as trees in a forest block your view of trees behind them. But even accounting for this, the calculation shows that every point in the sky should eventually be covered by the surface of a star. The whole sky should glow with the same intensity as the surface of an average star. This is not just a little bit brighter than what we observe. This is a sky as bright as the surface of the sun, in every direction, at all times. Day and night would be indistinguishable. The universe would be a blazing inferno. And yet, we look up and see darkness. The universe should be on fire, but it isn't. Olbers himself proposed a solution. Maybe dust and gas between the stars absorbs the light from distant sources, blocking it from reaching us. It sounds reasonable. We know interstellar dust exists. We can see it blocking light in certain regions of the Milky Way, creating dark lanes and patches where the stars seem to disappear. Maybe there's enough of this absorbing material scattered through the cosmos to block light from the most distant stars, preserving the darkness we observe. This solution held sway for decades. It seemed elegant, plausible, consistent with observation. But this doesn't work, and the reason it doesn't work reveals something important about the universe. The problem is thermodynamics. As the Scientific American pointed out in an analysis of the paradox, those dust clouds would heat up from absorbing all that radiation. Dust isn't a magic light sponge that can absorb unlimited energy. When matter absorbs light, it gains energy. When it gains energy, it heats up. When it heats up, it begins to radiate. This is just the second law of thermodynamics at work. Energy doesn't disappear, it transforms. The dust would absorb starlight and re-emit it as infrared radiation. As more and more light poured in from all those distant stars, the dust would get hotter and hotter. Eventually, it would reach thermal equilibrium with the starlight surrounding it. At that point, the dust clouds would be glowing as brightly as the stars they were supposed to be blocking. You haven't solved the problem, you've just delayed it. And an infinite universe is patient. Given enough time, everything reaches the same temperature. The dust becomes as bright as the stars. You're back to a sky ablaze. Some astronomers proposed other solutions. Maybe stars aren't distributed uniformly. Maybe they're clustered in ways that leave vast empty regions. Maybe the universe has some strange curved geometry that prevents light from traveling forever. Maybe there's something wrong with our understanding of light itself. None of these solutions worked. For decades, Olbers' paradox remained unsolved, an embarrassing thorn in the side of cosmology. The universe refused to obey the mathematics. The darkness mocked the infinite cosmos. And then, in 1848, the answer came from an unexpected source, a poet, a writer of horror stories, a man who had never looked through a professional telescope in his life. Edgar Allan Poe is remembered today for his macabre tales of horror and mystery. The Telltale Heart, The Fall of the House of Usher, The Raven. He invented the detective story with his character C. Auguste Dupin and helped establish the genre of science fiction. His life was marked by tragedy. His mother died when he was 2. His foster father disowned him. His young wife, Virginia, died of tuberculosis, and he struggled with poverty and alcoholism until his own mysterious death at age 40. But in the year before his death, Poe wrote something far stranger than any of his famous works. He called it Eureka, a prose poem, and he considered it his masterpiece. More important, he claimed, than Isaac Newton's discovery of gravity itself. On February 3rd, 1848, Poe delivered a lecture on cosmology at the New York Society Library. He had hoped for an audience of hundreds. Only 60 people showed up, and many of them were confused by what they heard. Poe was not presenting fiction. He was presenting his own theory of the universe, woven together from intuition, logic, and a remarkable capacity for scientific imagination. Most people ignored it. His friends found it baffling. This was the master of horror, the poet of the macabre, suddenly pontificating about the structure of the cosmos. Critics dismissed it as the ramblings of a man becoming unhinged. When Poe requested that his publisher print 50,000 copies, the publisher offered 500. Only a few dozen sold. Poe was devastated. He believed Eureka would transform human understanding of the universe. Instead, it vanished into obscurity, a curiosity in the bibliography of a famous fiction writer. But Eureka contained something remarkable, something that wouldn't be recognized for more than a century. In a passage that anticipated modern cosmology by nearly 100 years, Poe wrote, "Were the succession of stars endless, then the background of the sky would present us a uniform luminosity, like that displayed by the galaxy, since there could be absolutely no point in all that background at which would not exist a star." Poe understood Olbers' paradox perfectly. He saw the problem clearly, perhaps more clearly than many professional astronomers of his time. But then he offered a solution that no one else had considered. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions, would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us. Read that again, slowly. Pass each phrase. Poe was saying that space is dark because the universe is not infinitely old. The light from the most distant stars hasn't had time to reach us yet. The dark patches in the sky aren't empty. They're just too far away for their light to have arrived. This was 1848. Darwin hadn't yet published On the Origin of Species. The age of the Earth was thought to be just a few million years. The Big Bang wouldn't be proposed for another 80 years. Edwin Hubble hadn't yet proved that the universe was expanding. The cosmic microwave background wouldn't be discovered for over a century. And yet, somehow, Edgar Allan Poe, master of mystery and the macabre, intuited one of the deepest truths about our cosmos. The universe has a birthday. It came into existence at some finite time in the past, and that birthday is the reason the night sky is dark. How did he know? How could a poet, working with nothing but intuition and logic, arrive at a conclusion that would take professional cosmologists another century to accept? Poe himself claimed that Eureka came to him through a kind of cosmic intuition, a unity with the deep structures of reality that transcended ordinary reasoning. He believed the human mind contained within it an echo of the divine mind that created the universe, and that by looking inward, one could glimpse fundamental truths. That sounds like mysticism, not science. And yet, Poe was right. Edward Harrison, the astronomer who spent his career studying Olbers's paradox and wrote the definitive book on it in 1987 titled Darkness at Night, A Riddle of the Universe, acknowledged that Poe had arrived at the correct qualitative solution decades before the physics caught up. The poet saw what the scientists missed. In Harrison's careful historical analysis, he credits Poe with providing the first plausible solution to the paradox. The darkness of night is evidence of cosmic youth, and Edgar Allan Poe figured it out while writing his prose poem about the nature of reality. In 1901, Lord Kelvin, one of the most celebrated physicists of his era, the man who had helped establish the laws of thermodynamics and for whom the absolute temperature scale is named, published a paper that provided the first rigorous mathematical treatment of Poe's intuition. Kelvin was 80 years old and near the end of his career. He had spent decades thinking about the energy balance of the universe, about how stars shine and how long they can keep shining. In a lecture titled On Ether and Gravitational Matter Through Infinite Space, he showed that if stars have only been shining for a finite time, then the light from distant stars simply cannot have reached us yet. The mathematics were careful and precise, the kind of work Kelvin was known for. He demonstrated that even if the universe were infinite in space, it could appear dark if it had a finite history. The light from stars beyond a certain distance wouldn't have had time to arrive. This distance has a name, the cosmic horizon, and the region within it, the part of the universe we can see, has another name, the observable universe. Think of it this way. Light travels at about 186,000 miles per second, approximately 300,000 kilometers per second. Fast, yes, faster than anything else in the universe, but not infinite. Light has a speed, which means it takes time to travel. If a star is 1 light year away, the light we see from it tonight left that star 1 year ago. We're seeing that star as it existed in the past. If a star is 100 million light years away, we're seeing it as it existed 100 million years ago. Astronomy is always archaeology. We're digging through cosmic time every time we look at distant objects. Now, the universe is approximately 13.8 billion years old. We know this from multiple independent measurements, from the cosmic microwave background, from the ages of the oldest stars, from the rate of expansion of the universe. All these measurements converge on the same answer: 13.8 billion years, give or take a few hundred million. That means the farthest objects we can possibly see are those whose light has been traveling toward us for 13.8 billion years. Anything beyond that horizon is invisible, not because it doesn't exist, but because its light hasn't had time to make the journey. The universe simply hasn't existed long enough for light from those regions to reach us. This is the cosmic horizon, the edge of the observable universe. Beyond it lies more universe, possibly infinite amounts of it. But we can never see it, because the light from there will never arrive. And here's where it gets strange, because the universe has been expanding since the Big Bang. The space between us and distant objects has been stretching the whole time their light was en route. Because of this expansion, the actual distance to the cosmic horizon is not 13.8 billion light-years. It's about 46 billion light-years. The objects whose light we see after it has traveled for 13.8 billion years are now much farther away than they were when that light was emitted. But even accounting for this expansion, the observable universe contains a finite number of stars. about 200 sextillion, according to current estimates. That's 2 x 10^3, or 200,000,000,000,000,000,000,000. More stars than grains of sand on every beach on Earth. More stars than seconds that have elapsed since the Big Bang. It sounds like a lot, and it is. But it's not infinity. And that finite number, spread across the enormous volume of the observable universe, simply isn't enough to fill every line of sight with starlight. The dark patches in the sky are real. They're not optical illusions or blocked by dust. They're directions where no star has formed close enough for its light to have reached us in the 13.8 billion years the universe has existed. The darkness is the shadow of the Big Bang. The darkness is evidence that there was a moment before which nothing existed. The darkness is the signature of creation itself. But there's more to the story. The finite age of the universe is the primary reason space is dark. But there's a secondary effect that makes the darkness even deeper. An effect that wasn't discovered until the 20th century, and that transformed our understanding of the cosmos. In 1929, the American astronomer Edwin Hubble made one of the most important discoveries in the history of science. Working at the Mount Wilson Observatory in California, using what was then the largest telescope in the world, Hubble measured the light from distant galaxies and found something astonishing. Almost all of them were moving away from us. This wasn't just a few galaxies. It was nearly every galaxy Hubble could measure, and the pattern was unmistakable. The farther away a galaxy was, the faster it was receding. Hubble had discovered that the universe was expanding. This wasn't just the galaxies moving through space like shrapnel from an explosion. Space itself was stretching, carrying the galaxies along for the ride. The fabric of reality was growing, and everything in it was being pulled apart. Imagine dots drawn on a balloon. As you inflate the balloon, the dots don't move across the rubber. The rubber itself stretches, and the dots move apart. Each dot sees every other dot moving away from it, and dots that are farther apart move away from each other faster because more rubber is stretching between them. This is what's happening to the universe. Space is stretching, and this stretching has a profound effect on light. As light travels through expanding space, its wavelength gets stretched along with the space it's moving through. Blue light becomes green, green becomes yellow, yellow becomes red. Light that was emitted as ultraviolet shifts into the visible spectrum. Visible light shifts into infrared, and light that travels far enough from the most distant parts of the observable universe gets stretched so much that it shifts entirely out of the visible spectrum. This phenomenon is called cosmological redshift. The word redshift captures the essence. Light is shifted toward the red end of the spectrum, toward longer wavelengths. But for the most distant objects, the shift goes far beyond red. For the most distant objects in the universe, those near the cosmic horizon, this redshift is extreme. Light that was emitted as visible light billions of years ago arrives at Earth today as microwave radiation. It's still there. It's still carrying information about those ancient sources, but our eyes can't see it. It has been stretched beyond visibility. The cosmic microwave background radiation, discovered accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Labs in New Jersey, is precisely this: the afterglow of the Big Bang, stretched by the expansion of the universe from blinding visible light to a faint microwave hum. The story of its discovery is one of the great accidents in the history of science. Penzias and Wilson weren't looking for anything cosmic. They were radio astronomers testing a new horn-shaped antenna at Bell Labs facility in Holmdel, New Jersey. The antenna had been built for satellite communications to track and receive signals bounced off orbiting balloons. Now it was being repurposed for radio astronomy. But there was a problem. The antenna was picking up a persistent hiss, a steady, low-level noise that they couldn't eliminate. They tried everything. They checked every connection, every wire. They rebuilt parts of the receiver. They even climbed inside the antenna and scraped out pigeon droppings, thinking the birds might somehow be responsible for the interference. Nothing worked. The noise remained. It came from every direction in the sky, day and night, summer and winter. It was constant, uniform, seemingly everywhere. Penzias and Wilson were frustrated. They had a mystery on their hands, and they couldn't solve it. Meanwhile, just 60 kilometers away at Princeton University, a team of theoretical physicists was building a detector to search for something they predicted must exist: radiation left over from the Big Bang. Robert Dicke, Jim Peebles, and their colleagues had calculated that if the universe began in a hot, dense state, there should be a remnant of that heat still present, filling all of space, a cosmic background radiation with a temperature of just a few degrees above absolute zero. When Penzias heard about the Princeton work through a mutual colleague, he called Dicke. The Princeton team drove to Holmdel to see the antenna. They listened to the hiss. They ran the numbers, and they realized what Penzias and Wilson had found. It wasn't interference. It wasn't equipment malfunction. It wasn't pigeon droppings. It was the echo of creation itself. The cosmic microwave background radiation had been traveling for 13.8 billion years, cooled by the expansion of space from thousands of degrees to just 2.725 degrees above absolute zero. It was the oldest light in the universe. Light emitted about 380,000 years after the Big Bang, when the cosmos first became transparent. Penzias and Wilson won the Nobel Prize in 1978. They had, quite literally, heard the afterglow of the Big Bang, and that afterglow explains another layer of the darkness. The light from the early universe hasn't disappeared. It's still there, filling all of space, coming from every direction. But it's been redshifted so far that it's invisible to human eyes. We're bathed in the ancient light of the Big Bang. We just can't see it. So why is space dark? The answer has three parts, each contributing to the darkness we observe. First, and most importantly, the universe has a finite age. It came into existence approximately 13.8 billion years ago, and light from objects beyond a certain distance hasn't had time to reach us. There aren't enough stars in the observable universe to fill every line of sight. This was Poe's insight, formalized by Kelvin, and confirmed by everything we've learned about cosmology since. Second, the universe is expanding. Light from distant objects is stretched to longer wavelengths, shifting it out of the visible spectrum. The most distant visible light has been redshifted into the microwave range, invisible to our eyes, but detectable by radio telescopes. The expansion doesn't just make things darker, it makes them invisible. Third, stars haven't been shining forever. This might seem obvious, but it's crucial to the full picture. After the Big Bang, the universe was a hot, dense soup of particles and radiation. For about 380,000 years, it was so hot that atoms couldn't form. Electrons were constantly being stripped from nuclei by energetic photons. The universe was opaque, like being inside a star. When the cosmos finally cooled enough for atoms to form, a period called recombination, the universe became transparent. Light could finally travel freely. This is the light we see as the cosmic microwave background. But there were no stars yet. The universe was just hydrogen and helium gas, slowly cooling, filling the void. For the next few 100 million years, the cosmos was dark. Astronomers call this period the Cosmic Dark Ages. Then, somewhere between 100 and 200 million years after the Big Bang, the first stars began to form. Gravity pulled together dense clumps of primordial gas until the pressure and temperature at their centers became high enough to ignite nuclear fusion. These first stars were different from the stars we see today. They were massive, perhaps 30 to 300 times the mass of our Sun, because the primordial gas was warm and difficult to collapse. Only the largest clumps could overcome the gas pressure and form stars. These massive stars burned hot and bright, but they burned fast. They lived only a few million years before exploding as supernovae, seeding the universe with heavier elements. Slowly, over hundreds of millions of years, more stars formed, and those stars gathered into galaxies. The universe filled with light. But even then, even now, stars have finite lifetimes. They're born, they burn through their fuel, and they die. The process of star formation continues today, but it's limited by the amount of available gas and by the laws of physics. There simply hasn't been enough time for stars to have converted enough matter into light to illuminate the entire sky. The darkness we see is, in part, the darkness of a young universe still in the process of becoming. These three facts, finite age, expansion, and finite stellar lifetimes, combine to give us the dark sky we see each night. The paradox isn't really a paradox at all. It's only paradoxical if you assume the universe is infinite, eternal, and static. Once you abandon those assumptions, once you accept that the universe had a beginning and is evolving, the darkness becomes not just explicable, but inevitable. The night sky is dark because the universe is young. There's something deeply moving about this answer. For most of human history, people looked up at the night sky and saw eternity. The stars were fixed. The cosmos was unchanging. The universe just was, timeless, eternal, infinite. Generations lived and died beneath that unchanging sky. They tracked the stars, predicted the seasons, navigated by starlight. They built stories and religions around the constellations. They wondered at the darkness between the stars, but never thought to ask what it meant. The sky was simply there, as natural as breathing, as unremarkable as the air. The darkness was a given, a backdrop, a nothing that no one thought to question. But the darkness tells a different story. The darkness tells us that everything had a beginning, that there was a first moment, a first second, a first fraction of a second, when the universe came into existence, that before that moment there was no space, no time, no matter, no light, and that everything we see, everything we are, everything that has ever happened or will ever happen, traces back to that singular origin. The darkness is evidence of the Big Bang. This is what makes Olbers' paradox so remarkable. A simple observation, so simple it feels almost childish to point it out, leads directly to one of the most profound conclusions in all of science. The universe is not eternal. It has a history. It was born. Every time you look up at the night sky and see those patches of darkness between the stars, you're seeing proof that the universe began. You're seeing the finite speed of light inscribed across the heavens. You're seeing the cosmic horizon, the edge of what we can know, the boundary between the observable and the forever hidden. Consider what an extraordinary conclusion this is. For centuries, the most brilliant minds in science assumed the universe was eternal. They built their physics, their philosophy, their theology on this assumption. The cosmos had no beginning. Therefore, it needed no explanation for its origin. It simply was. But the darkness disproved them. The simple observation that the night sky is dark, something every human who has ever lived has experienced, was evidence all along that the universe had a beginning. The clue was there, embedded in the very fabric of night itself, waiting for someone to understand its meaning. This is one of the great lessons of science. Sometimes the deepest truths are hidden in the most familiar phenomena. We walk past them every day without noticing. The apple falls and Newton sees gravity. The compass needle points north and Maxwell discovers electromagnetism. The sky is dark and we learn the universe began. The resolution of Olbers' paradox also teaches us something about the nature of scientific progress. For centuries, people proposed wrong answers. Dust blocks the light. The stars are distributed unevenly. The universe has strange geometry. Each answer seemed plausible at the time. Each was wrong. The correct answer, that the universe has a finite age, required a complete revolution in our understanding of cosmology. It required abandoning the assumption of an eternal cosmos. It required accepting that the universe has a history, that it changes, that it began. Science doesn't always progress by small steps. Sometimes it requires leaps, the abandonment of entire worldviews, the acceptance of ideas that seem almost too strange to be true. The darkness of the night sky demanded such a leap. And in making that leap, we discovered something extraordinary about our place in the cosmos. But the story doesn't end there. Because even now, astronomers are still probing the darkness, still asking what it can teach us. The darkness of space has become a precision measurement, a tool for understanding the universe. In 2021, scientists used NASA's New Horizons spacecraft, the probe that flew past Pluto in 2015 and gave us our first close-up images of that distant world, to measure something called the cosmic optical background. This is the sum total of all visible light from all galaxies in the universe, filling the void between the stars like a faint cosmic glow. From Earth, this measurement is nearly impossible. Our planet is surrounded by dust, tiny grains of rock and debris scattered throughout the inner solar system. This dust scatters sunlight in all directions, creating the beautiful zodiacal light that you can sometimes see as a faint glow along the horizon after sunset. But that same scattered light washes out the much fainter cosmic optical background, making precision measurements impossible. But New Horizons is different. The spacecraft has traveled far beyond the inner solar system, now more than 7 billion kilometers from the Sun. Out there, in the cold void of the Kuiper Belt, the zodiacal light is virtually non-existent. New Horizons floats in a region of space 10 times darker than anything the Hubble Space Telescope can see from Earth orbit. In September 2021, scientists pointed the spacecraft's long-range reconnaissance imager, LORRI, toward patches of sky far from the Milky Way's disk, and took a series of careful images. They then digitally removed every known source of light: individual stars, nearby galaxies, scattered light from distant bright objects, even the heat glow from the spacecraft's own nuclear power source. What was left was the cosmic optical background, the faint, diffuse glow of all the galaxies in the universe, blended together into a uniform background light. The initial measurements were puzzling. The cosmic optical background appeared brighter than expected, about twice as bright as astronomers predicted based on adding up all the light from known galaxies. This suggested there might be some unknown source of light in the universe. Were there undiscovered galaxies hiding in the darkness? Some exotic physics producing light in unexpected ways? A new component of the cosmos that no one had considered? The mystery captured public attention. The universe, it seemed, was glowing more than it should. But in 2024, after years of careful analysis and new observations, the mystery was resolved. The extra light came from something much closer to home: galactic cirrus. These are wispy clouds of dust that lie above and below the plane of the Milky Way, illuminated not by any single star, but by the combined glow of our entire galaxy. Previous estimates had underestimated how much these faint clouds contribute to the background light. Once this foreground was properly accounted for using data from the European Space Agency's Planck spacecraft to map the galactic dust, the cosmic optical background matched exactly what astronomers expected. The brightness corresponded precisely to the sum of all galaxies that have formed and all stars that have burned over the past 12 billion years. The darkness of space, it turns out, is exactly as dark as it should be. No more, no less. There is something satisfying about this. After 4 centuries of puzzling over the darkness, after all the wrong answers and blind alleys, the universe makes sense. The darkness is comprehensible. We understand why it's there. And yet, the more we learn about the darkness, the more we realize how strange it really is. Because the darkness isn't just the absence of visible light. It's the presence of something else, something that makes up most of the universe, yet remains utterly invisible to all our instruments. We call it dark matter, and we call the force accelerating the universe's expansion dark energy. Together, they constitute roughly 5% of the cosmos. All the stars, all the galaxies, all the planets and moons and comets and asteroids, everything we can see, everything we can touch, everything made of atoms, makes up only about 5% of what exists. Think about that for a moment. The entire visible universe, hundreds of sextillions of stars, trillions of galaxies, the cosmic web of matter stretching across billions of light years, is a thin froth floating on an ocean of darkness we cannot see and barely understand. Dark matter was first proposed in the 1930s by the astronomer Fritz Zwicky, who noticed the galaxies and clusters were moving too fast. Based on the visible mass, all the stars and gas we could see, there wasn't enough gravity to hold the clusters together. The galaxies should have flown apart long ago, but they hadn't. Something invisible was providing the extra gravitational pull. We now know that dark matter forms a vast cosmic web, a scaffolding on which visible matter accumulates. Galaxies form in the densest regions of this dark matter web, clustering along its filaments, gathering in its nodes. Without dark matter, galaxies as we know them couldn't exist. The visible universe is shaped by invisible forces. Dark energy is even stranger. Discovered in 1998, when 2 teams of astronomers found that distant supernovae were fainter than expected, meaning they were farther away than predicted, meaning the expansion of the universe was accelerating. Dark energy appears to be a property of space itself. It pushes the universe apart, working against gravity. causing the expansion to speed up over time. We don't know what dark energy is. We don't know what dark matter is. We have mathematical descriptions of their effects, but no physical understanding of their nature. They are mysteries hiding in the darkness, waiting for future scientists to solve. The darkness we see in the night sky is filled with the darkness we cannot see, and that darkness shapes everything. Dark matter's gravity holds galaxies together, prevents them from flying apart as they spin. Dark energy pushes the universe to expand faster and faster, ensuring that the darkness will only deepen as the eons pass. In the far future, trillions of years from now, so far in the future that our current universe would be unrecognizable, the expansion of the universe will carry distant galaxies beyond the cosmic horizon entirely. Galaxies we can see today will fade from view. Their light will be stretched to infinite wavelength by the accelerating expansion, redshifted beyond detection, their existence erased from our observable universe. One by one, the distant galaxies will vanish, not because they've stopped existing, but because their light can no longer reach us. Eventually, only the galaxies gravitationally bound to our own, the local group, which includes the Milky Way, Andromeda, and a few dozen smaller companions, will remain visible. Everything else will have disappeared beyond the cosmic horizon, forever unreachable, forever unknown. And then, even those nearby galaxies will change. Over hundreds of billions of years, the Milky Way and Andromeda will merge into a single giant galaxy, sometimes called Milkomeda. The night sky will show a brilliant band of stars from this merged galaxy, but nothing else. The darkness beyond will be absolute. Eventually, even those stars will burn out. The last red dwarfs, tiny, miserly stars that sip their hydrogen fuel over trillions of years, burning so slowly that they can shine for 10 trillion years or more, will finally exhaust their supply and fade to black. No more stars will form, because all the gas will have been locked up in stellar remnants and cold brown dwarfs. The universe will enter what cosmologists call the heat death, a state of maximum entropy, where everything is cold and dark and nothing interesting can ever happen again. The last protons may eventually decay, 10 to the 40th years from now. The last black holes will evaporate through Hawking radiation, 10 to the 100th years from now. And then there will be nothing but a cold, empty void, expanding forever, cooling toward absolute zero, silent and dark for all eternity. This is the ultimate fate of the darkness. It doesn't just surround us. It waits for us. In the end, it wins. But that ending is unimaginably far in the future, so far that human minds can barely conceive of it. The sun won't run out of fuel for another 5 billion years. Complex life on Earth has existed for less than a billion. Human civilization is only a few thousand years old. We are at the very beginning of cosmic history, not the end. In fact, there's something remarkable about the timing of our existence. We live at a unique moment in cosmic history, a moment when the universe is old enough for galaxies, stars, and planets to have formed, but young enough that the cosmos is still filled with light. A moment when the universe is transparent enough to see distant galaxies, but not yet expanded so far that they've disappeared beyond the cosmic horizon. If intelligent beings had evolved a few billion years after the Big Bang, the universe would have been chaotic and inhospitable. No heavy elements for rocky planets, no stable stars for warmth. If they evolved trillions of years from now, the universe will be dark and cold. No visible galaxies, no new stars, no energy sources for life. We exist in the Goldilocks zone of cosmic time. Not too early, not too late. The darkness of the night sky is proof of this. It shows we live in a universe young enough for darkness to still exist, old enough for stars to have formed. Some philosophers have called this the temporal cosmological principle, the idea that we exist at this particular time because this is the time when beings like us can exist. The darkness is part of what makes life possible. In a universe blazing with infinite light, the universe of Olbers' paradox, the temperature would be so high that life as we know it couldn't survive. The darkness keeps us cool enough to exist. Right now, in this brief cosmic moment between the Big Bang and the heat death, the universe is alive with light. Stars are being born in stellar nurseries across billions of galaxies. Massive clouds of hydrogen are collapsing under their own gravity, heating up, igniting nuclear fusion, beginning their journey from dark gas to brilliant star. Planets are forming in the accretion disks around young suns, accumulating from dust and rock, becoming worlds. And on at least one of those planets, a small blue world orbiting an ordinary yellow star in an unremarkable spiral galaxy, life has emerged and begun asking questions. We are the universe asking questions about itself. We are matter that has become aware, looking out at the cosmos and wondering why it exists, why it looks the way it does, why the sky is dark at night. And in 400 years of asking that question, from Kepler to Olbers, to Poe, to Penzias and Wilson, to the New Horizons spacecraft floating in the darkness of the outer solar system, we have learned something profound about our cosmic home. Why is space dark? It seems like such a simple question. A child might ask it. A toddler, looking up at the night sky for the first time, might point at the darkness between the stars and say, why? But the answer took 400 years to discover, and it required us to overturn our most basic assumptions about the nature of reality. The universe is not infinite and eternal. It had a beginning. It is expanding. It is changing. And it is finite. At least, the part we can see is finite. The darkness tells us all of this. The darkness is the signature of the Big Bang, written across the sky in letters of absence. Every black patch between the stars is a testament to the finite age of the cosmos, to the speed of light, to the expansion of space, to the fact that there was a first moment and there will be a last. For most of human history, people looked up at the night sky and saw eternity. The stars were fixed points of light, unchanging across generations. The constellations that the ancient Greeks named are still recognizable today, thousands of years later. The cosmos seemed permanent, eternal, infinite, a stage on which human dramas played out, but itself immune to change. Philosophers from Aristotle to Newton assumed the universe had always existed and would always exist. It was simply there, a given, a backdrop to existence. This assumption shaped everything from theology to physics. If the universe was eternal, it needed no creator. Or if it had a creator, that creator was not a builder, but a sustainer, maintaining an already existing cosmos. But the darkness told a different story. The darkness was a clue, hiding in plain sight for centuries, waiting for someone to ask the right question. Why is the sky dark at night? Such a simple question, such a profound answer. The universe began. This single fact, implied by the darkness of the night sky, transforms everything. It means the cosmos has a history, a narrative, a direction. It means there was a first moment, and there will be a last. It means we exist not in an eternal present, but at a particular moment in cosmic time, a moment after the beginning, but before the end. And that moment, it turns out, is special. We live in the stelliferous era, the age of stars. For the first few 100 million years after the Big Bang, there were no stars, just cooling gas and expanding darkness. For the next hundreds of trillions of years after the last stars die, there will be no stars, just cooling remnants and eternal night. We exist in between, in a brief window of cosmic time when matter has organized itself into brilliant nuclear furnaces, flooding the universe with light. The darkness between the stars is a reminder that this window is finite. Stars are not eternal. The universe is not eternal. Everything has a beginning and an end. When Heinrich Olbers looked up at the night sky in 1823 and asked why it was dark, he couldn't have imagined where the question would lead. He was a physician in Bremen, treating patients by day, gazing at stars by night. He didn't know about the Big Bang. He didn't know about expanding space. He didn't know that his simple question would help unlock the deepest secrets of the universe. But it did. Through Edgar Allan Poe and Lord Kelvin, through Edwin Hubble and the discovery of the expanding universe, through Arno Penzias and Robert Wilson and the echo of the Big Bang itself, the question of the dark night sky became one of the most important questions in all of cosmology. The darkness of space is not emptiness. It is not nothing. It is one of the most information-rich phenomena in all of nature, encoding within it the history and structure of the cosmos. Every time you look at the dark sky and wonder why it's dark, you're asking a question that leads directly to the Big Bang. Tonight, if the sky is clear, go outside and look up. Find a place away from streetlights if you can. Let your eyes adjust to the darkness. It takes about 20 minutes for your pupils to fully dilate and your retinal chemistry to shift into night mode. Be patient with the process. The darkness reveals itself slowly. See the stars scattered across the black. Each one is a sun, some smaller than our own, some giants that would swallow the orbits of all our inner planets. The nearest one, apart from our sun, is Proxima Centauri, about 4 light years away. The light you see from it tonight left that star 4 years ago, back when you were living a different life, thinking different thoughts, unaware of this moment. See the Milky Way. If you can find it, that band of light stretching from horizon to horizon is our galaxy seen edge on, 100 billion suns smeared across the sky by distance. Everything you can see with your naked eyes, every star, every planet, every constellation lies within this one galaxy. The universe is larger by a factor of 1 trillion. See the darkness between the stars, those vast stretches of apparent nothing. In those patches of black, there is no star close enough for its light to have reached us in 13.8 billion years. Some of those directions may have stars, but they're beyond the cosmic horizon, forever invisible. Others may be genuine voids, regions where matter never accumulated, where no stars ever formed. And know what that darkness really means. It means the universe was born. It means there was a moment, 13.8 billion years ago, give or take, when everything that exists came into being. Before that moment, there was no space, no time, no matter, no energy. And then, suddenly, there was. The darkness means light has a speed. It takes time to travel, even at 300,000 kilometers per second. The universe is so vast that light from distant objects takes billions of years to reach us, and some light will never reach us at all because the universe hasn't existed long enough. The darkness means space is expanding. The very fabric of reality is stretching, carrying galaxies apart, red-shifting ancient light into invisibility. The universe is not static. It's alive, dynamic, evolving. The darkness is not the absence of something. It is the presence of a limit. The limit of time, the limit of light, the limit of what we can ever hope to see or know. And in that limit, paradoxically, there is a kind of comfort. The universe is not infinite and eternal and unchanging. It is finite and young and alive. It had a beginning, which means everything that followed, every star, every planet, every molecule of your body came from somewhere, came from something. In a strange way, the darkness is comforting. An infinite, eternal universe would be incomprehensible. A static canvas without meaning or direction, stretching forever in all directions, unchanging for all eternity. We would be lost in that cosmos, truly insignificant, truly alone. But a universe with a beginning has a story. Stories have meaning. Stories matter. And we are characters in that story. Perhaps minor characters, perhaps major ones. We can't yet know. But characters nonetheless. The darkness tells us that we are part of something larger, something with direction, something that began before us and will continue after us. We emerged from the cosmic darkness, assembled ourselves from stardust, evolved consciousness, and looked up at the sky to ask why it was dark. And in asking that question, we discovered where we came from and where we might be going. The atoms that make you up were forged in the hearts of stars that lived and died before the sun was born. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was synthesized in stellar furnaces billions of years ago, scattered across space by supernova explosions, gathered up again by gravity into new stars and planets. You are, quite literally, made of stardust, made of light that burned before there was an earth to receive it. The darkness of space connects you to the Big Bang. Every time you see it, you are seeing the boundary of creation itself. You are seeing proof that the universe began, that time has a direction, that existence has a story. And maybe that's the most profound answer to Olbers's paradox. The night sky is dark because the universe is young enough and small enough and new enough for darkness to still exist. We live in a cosmos that is still becoming, still evolving, still full of possibility. The darkness is not the end of the story. It is proof that the story is still being written. Somewhere out there, beyond the cosmic horizon, stars are being born that we will never see. Galaxies are forming that will never send their light to Earth. Worlds are taking shape around alien suns, perhaps hosting life that will look up at their own dark skies and wonder, just as we do, why the void is black. The darkness connects us to all of it. The darkness connects us to all of it. To the birth of the universe, to the future we cannot see, to the vastness of everything that exists beyond our horizon of knowledge. The darkness is not empty. The darkness is full of everything we have yet to discover. Every patch of black sky holds mysteries we haven't solved, questions we haven't asked, wonders we haven't imagined. The darkness is not an ending. It is an invitation to keep looking, keep wondering, keep exploring. 400 years ago, Johannes Kepler looked at the darkness between the stars and saw a puzzle. Today, we look at that same darkness and see an answer, one of the most beautiful answers science has ever given us. The universe began. The universe is young, and we are part of its story. Look up tonight if you can. Find a place away from the lights of civilization. Let your eyes adjust to the darkness and see the sky as Kepler saw it, as Olbers saw it, as Poe saw it, not as a backdrop, but as evidence. Evidence of the Big Bang, evidence of cosmic history, evidence that the universe began and that you are part of its ongoing story. The darkness is not nothing. The darkness is everything. Look up. The darkness is trying to tell you something. It's trying to tell you that you exist in a universe with a beginning, a middle, and someday an end. That you are part of a cosmic story that started 13.8 billion years ago and will continue long after you're gone. That every moment of light is precious because it emerged from darkness, and to darkness it will eventually return. That the universe is not indifferent to your existence. The universe made your existence possible by being exactly the age and size and shape it is. In a different universe with different properties, you could not exist. The darkness is one of those properties. The darkness is necessary for life. The question, why is space dark, turns out to be the same question as why is there anything at all? And the answer to both is the same. Because the universe began. Because once there was nothing, and then suddenly, gloriously, impossibly, there was light, and the light is still spreading, and the darkness is still there at the edges, marking the boundaries of what has been and hinting at what might yet come. We finally know why space is dark, and the answer is beautiful. It tells us that we are not lost in an infinite, eternal, unchanging void. We are not specks of dust in a meaningless cosmos. We are part of a story with a beginning and a middle, and someday an end. A story that includes us, that made us possible, that we are still writing with every question we ask and every discovery we make. The 400-year journey from Kepler's first inklings to our modern understanding of cosmology has been one of the greatest intellectual adventures in human history. It began with a simple question: why is the night sky dark? It led through the work of countless scientists, some famous, some forgotten, each adding a piece to the puzzle. It required overturning our deepest assumptions about the nature of reality, and it ended with a discovery that transforms how we see ourselves and our place in the universe. We are children of a young cosmos. The universe that made us is still in its infancy, still growing, still evolving, still full of possibilities we can barely imagine. The darkness between the stars is not emptiness. It is potential. It is mystery. It is the unwritten chapters of a cosmic story still unfolding. The darkness is not our enemy. The darkness is our teacher. It has been trying to tell us about the universe for 400 years. And finally, we have learned to listen. Go outside tonight. Look up. See the darkness and understand what it means. You are home.